So, good evening, ladies and gentlemen. And in this stream, we will be continuing our study of the greedy principles in CP and in data structures and algorithms and overall in programming. And yes, and yeah, in the previous stream, we had solved these two problems, and our aim is to solve as many problems as possible today. As you've seen, we have solved. Okay, yeah. As you've seen, we have solved 1193, and here's the code. And yes, so this is it. Yeah, we'll continue. And the next problem is 10,020. 10,020. Okay, that's interesting. I guess we are logged now. Yeah, minimal coverage. Let me recheck the question name. And yes, the question name is indeed minimal coverage. And let's continue. Minimal coverage. Given several segments of line I'm assuming this is in the x-axis with coordinates LI, you have to choose the minimal amount of them such that they would completely cover the segment 0 to m. The first line is the number of test cases, followed by a blank line. Each test case is in the input should contain an integer m, followed by the pairs LI, where Li and Ri are smaller than 50,000 and I is smaller than 1 lakh or 100,000. Each on a separate line. Each test case of input is terminated by pair of 0, 0. Each test case will be separated by a single line output. For each test case, in the first line of output, for each test case, in the first line of output of what the hell they have written, your program should print your program should print the minimal number of line segments which can cover the segment OM, and the following lines the coordinates of segments are sorted by their left and Li should be printed in the format as in the input. Okay, that's interesting. Your program should print 0. Okay, if 0 comma m cannot be covered by line segments, your program should print 0 without quotes. Print a blank line between the two outputs for two consecutive test cases. Okay, number of test cases. Okay, fantastic. Okay, so I will cover the general theory if someone is new to this principle. Yeah. So basically, I can say that I have two boundaries. The first boundary being 0 and the second boundary being m. This is 0 and this is m. And we have several intervals. I'm calling this intervals because, yeah, that's the standard way of seeing line segments in the greedy approach. And we have several intervals. I have to choose a minimum number of line segments such that the complete interval has been, covered. Yeah. So yes, now I would like to propose a border. Okay. Yeah. First of all, yeah. First of all, we are going to sort. I'm not going to prove this again because this will be the third time I'm proving the same thing. But yeah, in the morning stream, I have solved a similar question of intervals. I would rather say I have solved similar two questions. And yesterday I have solved in the yesterday's video I have solved lead code question number 45, which gives us a gist of the greedy algorithm. And yeah, In the question UVA 10328, we have solved a similar problem. So yeah. Now I would like to introduce. Now we have to choose some what shall I say? We have to choose some intervals or line segments in this case, uh, which have starting point below, which has starting point less than 0, less than or equal to 0. Now you may ask why? Because if it's not the case, then we are going to leave some area, and yeah, that's not given in the question. So yeah, so I would like to ask you, which line segment should I choose? And the answer is these. And the answer can be this line segment, or this line segment. Now, let me focus on the starting point. Uh, as we have grouped the line segments which can be chosen, I would like to ask which line segment should be actually chosen. And uh, now now logically in the common sense, which line segment would you like to choose? And your answer would be the line segment which ends towards the right hand side the most, or which has a greater ending point. Why? Because this is the relevant area which we have to cover. And let's say regardless, now you may think that this length segment uh, is greater in length as compared to these length segments, but the thing is, this line segment is not useful because it is not providing future feasibility. So yeah, now I'm assuming that this line segment is has a greater ending point, so I will draw another border over here. Yeah, so we have created a new border. So we have created a new border, and now in order to extend this line segment, we want another line segment which has a starting point smaller than or equal to this border. Let's say this border is at uh, you know at x coordinate equal to 2. So what can be our possible solutions? These two line segments. And by observation, you would understand that this line segment should be chosen. So yeah, I will draw another dotted line. Now assume that this line segment is just touching this line, and I would like to ask which line segment should be chosen. Assuming that this is at assuming that this is at index 4, or not x coordinate 4. Now this can be the option and this can be the option, and as this ending point is more towards right, so this is the line segment which should be chosen. Isn't it? Let's draw a dotted line once again. And now here we are. Um, we can choose either this or this. Just assume for a minute that the ending points are the same and the starting points are different. This has a greater length than this one. But regardless, as we have to just consider the ending points. So even if you choose this as the next line segment, it's okay. Here we will be having another section, and let's say this is this is the, let's say, x coordinate equal to 6. Now we can choose either this or this, and obviously, what should be our choice? It would be this. Why? Because we are having this line segment is having greater ending point. So it provides future feasibility. So yeah, this will be the new border, I would like to say. Let's say this is let's say this is of size 7. Let's say this is 8. Now only one line segment can be chosen, and yeah, it would be obviously this line segment. So now the farthermost point which can be reached is this. And here we can say that this, let's call it farthest point. Farthest point is greater than equal to m, isn't it? So yeah, we have covered the entire interval with minimal number of choices. So what's the minimal number of choices? The choices are 1, 2, 3, 4, 5. Okay, 1, 2, 3, 4, 5, 6, 7. So we have chosen 7 lines, and this will cover the entire interval. Now let's say if for some reason let's say this line segment didn't exist. Now out of these, uh, we are not what can we say? Let's say even this line segment didn't exist. Now as you can see that there's a gap between these two. So this gap cannot be fulfilled no matter what. So yeah, in such a case where we are not getting any line segment which has its starting point smaller than equal to the instant border, then we can say that the patch between 0 to m cannot be covered whatsoever. So yeah, this is the intuition. And if you have been following the streams and the videos since the last 24 hours, this question would be quite easy to you. Okay, 10,020. Yeah, okay. For each test, okay. Let me read the input. Each on a separate line. Okay, yeah. I guess I have to use SS stream. Um, take the input for this question. Let's include SS stream, isn't it? The first will be int m. Then we have a bunch of li. Int pair of int comma int. Okay, they should have given at least how many segments are there, isn't it? Mm-hmm. In the end, it's him and I. I have to somehow figure out. Yeah. Okay. And there's a blank line between these two. So yeah, that helps. SS stream C++. Let's check string stream, both input output. Okay, ss str, ss num. Okay, yeah. Extract the integer and store it in them. Okay, yeah. So here is how we are going to mm, take the input. Okay, create a string stream object initialized with str. Okay, string stream initialized with ss str. So here we are, and not str. Yeah, and string str. Okay, um okay, I would like to say while I'm going to take the input in str while it's not empty. And yeah, and how we are going to convert it? Yeah, we're going to ss. Let's say int li ri ss li and ri arr dot pushback li ri, isn't it? That's the case. And just for my sanity, uh, I haven't used ss stream since long. I would like to check if I am mm, okay, where 0, should not be printed. Okay, in the following the coordinates segment sorted by LIRI. The coordinates okay, just a second. Each case of input is terminated by pair of 0, 0. Okay, we don't have to do this circus of okay. Li while true into LIRI. Take the input of LIRI. Fantastic. If both of them are 0, I'll simply break. Otherwise, I will push it as a pair. Um, I'm going to sort this array. Array.begin, array.end, and I need a comparator function. Let's declare this comparator function. Int num1. Let's int. No, not int. Pair of int comma int even pair of int comma int p2 return p1 dot first is smaller than p2 dot first. Yeah, this should do. And as we were discussing, we will create a different function. I guess we have to actually print. Yeah. Um. Okay. A pair of int comma vector of int comma int. Yeah. Um. Cover get minimal coverage. And yes, what will be our input? Our input will be just uh, the array. And the details of the array we are getting from the question, ARR. And yes, count equal to 0. We'll have int I and d equal to 0. We have border equal to 0, as we have to cover the range 0, m. We also take the input m. You know what? Let's keep this m. Okay, and yes, while I and d is smaller than ARR size, now I will find out the ending point. Ending point initially will be -1, and not ending, farthest point I should say. Farthest point. Bool farthest point set is false, as we haven't gotten the farthest point, while and is smaller than ARR, that says and ending point is equal to ARR IND dot second, not ARR. Oh my goodness, not ARR IND dot second. We are going to compare it with border. ARR IND dot first should be smaller than equal to border. If it is, if farthest point set, if farthest point is not set, yeah, then I would say farthest point equal to ARR IND dot second farthest point set equal to true. Else, I would simply say farthest point equal to maximum of farthest point comma ARR IND dot second. Yeah. After this, I would like to increment my count and I also have to print the starting point, I should say. Starting point is equals to -1. Let's say initially, and then starting point shall be ARR IND at first, regardless. Regardless, I shall keep it in the array. Yeah. If farthest point is not set, then I'll simply return okay. Let's call it answer. Simply return -1 comma answer. Yeah. As we can't cover the internal farthest point set, I should say. If this farthest point, yeah. And one more thing, I'm going to push back answer dot push back starting point comma farthest point. Oh, I'm making a mistake over here. Yeah, farthest point starting point shall be here and here. Of no, that's not the case. If now I am going to replace this line with if farthest point is smaller than ARR IND at second, then I would say farthest point equal to ARR IND at second and starting point equal to ARR IND at first. If farthest point is greater than equal to m, then simply return 0 comma answer. 0 represents success. And at the end, if we are outside this array, then I will also return -1 because even after iterating to the complete array, we are unable to reach the to reach or cover the m till n, and yeah, that's why. Okay, pair of int comma vector of pair of int comma int answer is equals to get minimal coverage. If answer dot first is equals to -1, then I would print 0. That's it. If that's not the case, then I would print mm, answer that second that size. Yeah, and I will print the entire array int pair of int comma int in. Okay, one thing which we have given is that should be printed in same format as input. So we have to print each and every interval in a new line. Yeah. After that, if t is greater than 0, one extra line should be printed. Let's hope that we have implemented a correct function and we have made a mistake. We're making a mistake somewhere. First of all, I would really like to check if I taken the input correctly. P dot first. I like to print this in curly braces. Yeah, and yeah, -5 -3 -1 0 and 2 comma 5. Okay, so we are stuck somewhere in get minimal coverage. And for this, oh yeah, we are not updating the border. Border should be equal to farthest point. That's oh my goodness. I'm not incrementing IND. Okay, we'll just not print this, and here is our answer. Let's hope that this problem will get an easy. Okay, yeah, fantastic. Let's head watering grass. Yes, 10,382. Um, we have already covered this problem, and we won't be covering it again. 11,264. This seems to be an interesting question as they highlighted it using the blue text, and this star over here as well. 11,264. 11,264. Yeah, okay. What? That's so cool. Okay, just a second. Let me take a sip of water. Yeah, let's read the question. UVA 11,264 coin collector. Our dear Sultan is visiting a country where there are n different types of coins. He wants to collect as many different coins, as many different types of coins as you can. Now, if he wants to withdraw X amount of coins from the bank will give him his money using the following algorithm. If X is equals to 0, return. Let Y be the highest valued coin that does not exceed X. Give the customer a Y valued coin. Withdraw X minus Y. Now Sultan can withdraw any amount from the bank, any amount of money from the bank. He should maximize the number of different coins that he can collect in a single withdrawal. Okay, we are talking about different number of different coins. Okay, input. First line of the input contains t number of test cases. Okay, each of the test case starts with n equal to n which belongs to the range 1 to 1000. uh, the number of different types of coins. Next n line contains n integers c1, c2, cn, the value of each coin type. Okay, okay, so yeah, c1 equals to 1. Fantastic. And this one is important. For each test case output, one line denoting the maximum number of coins. The Sultan can choose in a single withdrawal. He can withdraw infinite amount of money. Okay, so I would like to discuss this test case. I guess I've spotted the required pattern, but let's move on. I'm going to what shall I say? Okay, let's start with one. Let's change the color. 1, 2, 4, 8, 16, and 32. So in order to choose 32, the amount should be greater than equal to 32. So yeah, 32. Next amount he should choose 16. So yeah, the amount should be greater than equal to 16, isn't it? Then he can choose 8, 4, 2, 1. Now I would like to ask, why is this feasible? No, no, no. I guess I have made a mistake. 8 plus 4, 8 plus 4, 12, 12 plus 2, 14, 15. Yeah. So the resultant amount will be, this can be written as 16 into 2. This can be written as 16 into 1. And this can be written as 8 plus 4 is 12, 12 plus 4. What is 12 plus 4? What am I saying? What is 12 plus 2? 4? What am I saying? 12 plus 2 is 14 and plus 1 15. So yeah, 16 into 1 minus 1. So 16 into 2 plus 1, that is 4 minus 1. And the answer is 16 for the 64 minus 1, 63. Now I would like to ask um, you a question. After take, first of all, 63 is greater than 32. So after taking 32 from 16, what will be the resulting value? The resulting value will be 62 minus 63 minus 32. It will be 31, which is smaller than 32. Yeah. Now I'm going to take 16 out of it. So the answer would be 15. 15 is smaller than 16. Again, I would like to take out, what shall I say? 8. So the answer will be 7, smaller than 8. So I can't even pick 8 again. Then I will choose. Then I will remove 4. Then I will remove 2. Then I will remove 1. We have reached the end over here. But something interesting happens during this test case. 1, comma 3, comma 6, comma 8, comma 15, comma 20. Now let's take the summation of all this, because why not? Yeah. 1 plus 3 is 4, 10, 18. 18 plus 15 is 33, plus 20 is 53. So yeah, this is the amount which we are dealing with. After taking, what shall we say? After taking 20 out of this 53, we will be having 33. But the thing is, this 33 is greater than 20. So I can take 20 again from this 33. So I will be having 13. Now it is smaller than 20. Okay, so I have picked this coin. Now 13 itself is smaller than 15 again. So I can pick only 8. So 13 minus 8 is 5. So the remaining amount is 5. I have picked 8 as well. 5 is smaller than 6. So I have to use, what can we say? Uh, Coin with the denomination 3. So 5 minus 3 will get 2, which is smaller than 3 itself. So I have used 3 as well. And as none of the coins is, you know, what can we say? Greater than equal to, sorry, as the remaining coin is 1, and yeah, we will pick two 1 coins, and we have used the 1 coin as well. Now, why is this happening? Now, I would like to shed some light upon the condition which is there in this case, which is missing in this case, but was present in the previous test case. Yeah. So 1. Let's write the instant amounts. 1 plus 3. 1 plus 3 is 4. 6 plus 4 is 10. 10 plus 8 is 18. Uh, 18 plus 5. 8 plus 5 is, yeah, 33. 33 plus 20 is 53. Now I would like to say one thing. Um, I can't use after 2015 because after subtracting 20 from 53 there's 33, and 33 itself is what can we say, uh, greater than 20, isn't it? So I won't use, yeah, so I can't use 15, so I can't use 15, as I can't use 15. Do we have to actually implement a simulation or something? I can't think of a solution. I can think of a solution. I can think of a proof as of now. Okay, let's say um okay, let's say the highest value denomination. Okay, in order to pick 15, um yeah, in order to pick 15, the remaining amount should be either should have two conditions. It should be uh, greater than equal to 15, and um this amount which we are talking about should be smaller than the next higher denomination. Now let's say, mm, one thing which I can say for sure is that in order to pick 20, I need 20 minimum. It's okay. Forget about this. What's a number? Um, what are the valid numbers then? Okay. So 15, 16, 17, 18, 19. Yeah. These are the only valid numbers. Um, if reached, these are the only valid numbers uh, which will absorb the value of what can we say, 15. Talking about 8, uh, any value which is smaller than 15 but greater than equal to 8, that is 8, 9, 10, 11, 12, 13, 14, 15, 13, 14. Yeah, if this is this is the amount which we want, then we'll for sure need 8. Okay, and so on. Okay, so this is one of my observation. As you have seen that after simulating that I have the summation of all these coins as my initial value which I want from the bank, and it indeed gives a correct answer for both of these test cases, but I don't have any proof, and I can't think you know, of anything. So let's say in order to pick 15 and 20 both, I have to at least pick, I have to first initially have 20, yeah, then I have to, have a remainder of just, mm, what can we say? Yeah, if I have 35 rupees, then I can pick 20, I can pick 15, and I will be happy. But, um, I can say I also want to, I also wish to have 8. So, what will be my condition? So, as now we were discussing that, uh, the minimum coin, the minimum denomination required to collect both the coins of value 20 and 15, these numbers should be 35. Now, there's no way, to include, and I wish to collect the coin with 8 value. Let's call it rupees as of now. I also have to collect 8 rupees. Naturally, what one can think of is that 20 plus 15 plus 8. The remainder shall be 33. But one thing which you can see is that after taking out 20 from 33, um, I have remainder as 13. 13, 20 plus 25 is 35 plus I have a remainder of 18. No, no, no. What am I smoking? Okay, let's say I have to collect, okay, 35, 35 plus 8. What is 35 plus 8? Yeah, 35 plus 8 is 43. After collecting 20 from 43, I will still have 23. But as you can see, 23 itself is greater than or equal to 20. So we have to again collect 20, not 15. So it's practically impossible to collect all of these 3 coins together. Yeah. But I can safely say that I can either collect 8 or either collect 15 as per my convenience. Let's say I wish to collect let's say I wish to collect 20, 15 and 6. And I can't do that as well. Why? Okay, one thing which you can notice is that whenever I touch the sum of what shall we say? Let's say 15 plus 8 is greater than 20. 15 plus 6 is greater than 20. And 15 plus 3 is smaller than 20. So let's say I have to pick 3, 15 and 20. I can say that, 3, 15 and 20. So we will have 38 rupees, let's say. So I can pick 20. Remainder will be 18. Then I will pick 15. I will pick 3. So what you can see is that whenever the summation of the, let's say, previous denominations exceeds, uh, let's say, the highest value which we are talking about, 20, then we have to pick 20 again. Yeah. That's all right. Let's say, okay, let's now we have to pick um a few of these elements, not few, the maximum number of elements such that we don't violate this condition. Let's say I pick one, I pick three, four. Now four is indeed you know smaller than six, so I can take six as well. So 10, but 10 is greater than 8, so I can't pick 8 again. Now you may ask why, because let's say 18 is the total denomination. So I would use 8 twice and I would use 1 twice. So as of now you can see we have 10. 10 is smaller than 15, so I can pick 15 as well. 10 plus 15 is 25, and yeah, 25 is greater than 20. Okay, so I guess I have figured out um but we can have multiple starting points, don't we? Why? Hmm, starting from the left and picking the coin then and there itself benefits us. I don't know. Let's think about this a bit. Let's say I'm at 1 and I don't pick 3 then and there itself. Then am I violating some sort of future feasibility? One may think, yeah, you're not picking the element which can be chosen, and you might be damn right. Okay, let's think of only 3 elements. I'm at the first element. I will choose the first element because one can be chosen each and every time. That's for sure. You may ask why? Because we can have a remainder of one in each and every addition of cases. You know what I mean? If I didn't have one, then some of the test cases won't. Some of the money can't be borrowed. If you know what I mean. I will choose one. If I don't, let's say, if I don't choose the second element, then I am I'm sure that I can choose the third element, but it's of no use. Why? Because even though by skipping the first element, um, even after skipping the first element, I have not ensured that I will be getting more coins. I will be collecting more coins. If I choose the second element, the if I can pick the third element, then I shall pick the third element as well. Now this instant summation which we are talking about should be as small as possible, isn't it? So I guess that's my theory. As this let's say this instant summation increases, then it destabilizes the future stability, feasibility that of picking some more coins. Yeah. So due to this simple reason, I'll be trying to implement a greedy algorithm. our thinking is not the the clearest, I should say, but it's worth a try. Question number is 11264. Let me rename. Yeah, this is a classic code forces type input. We'll have an, we will take an. Yeah, after that we'll have count as equal as 1 and instant sum as well, and then we'll start our journey. If instant sum is smaller than ARR of I, instant sum plus ARR of I or plus plus. We will, I guess, surely get the correct answer for the given test cases, but I'm sort of worried about the judge, the actual test cases in the database. Yeah, let's submit. Okay, wrong answer. Fantastic. As our thought process was not clear enough, you can withdraw infinite amount of money from the bank. This is okay. Let's take a few test cases. Let's say I have 1, 2, 1, 2, 5, 10, 20. I can't, pick any of the value which is directly equal to these. Let's say if I have to pick 10, 50, 10, 5, I will pick 15, 17, 18, 13. Just from the naked observation, it feels that each and every coin can be picked because after, let's say we have 38, then we'll subtract 20, then we'll have 18, then we'll have 10, one more coin, then we'll have 8, 5, one more coin, and then we'll pick, we'll have 3, pick 2, one more coin. So we'll be picking each and every coin. Let's say I change something. Let's say if I say The coins are of denomination 1 to 5, and let's not 5, it's 8, comma 10, comma 20. One thing which is for sure, in order to pick 10, yeah, if I choose 19, let's say if I choose 19, answer will be this. Um, yeah, this is an interesting question. For each Tuskers output, denoting the maximum number of coins Sultan can collect in a single withdrawal. Mhm. Um, oh my god, what was that? Oh my goodness. This is some Chinese guy, I suppose. What is this QR code, man? Yeah. I guess I should have read the complete paper. In order to pick a certain coin, what shall be the condition? Okay, I'm going to, um, you know, let's say, okay, first, okay, I'm going to do something interesting. La 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 la. Mm-hmm. See, in ARR of I, let's see, let's check if int withdraw, we have int x, if x is equals to 0, we return 1. Yeah, int I and int, not I will get number of coins. Get number of coins, we have vector int ARR, we have IND, we have what shall we say, um, um, total value, let's say value, I would say total value. int IND equal to ARR that size minus 1. Um, int value equal to total value, while value is greater than 0. I would like to, mm, what can we say? Well, ARR of IND is smaller than equal to value, let's say. I would like to decrease the value by ARR.IND. Int count is equals to 0. And yeah, I would say IND minus minus um, count plus plus return count. I shouldn't say that this the variable the name is instant sum. Yeah, fantastic. Okay, so what's the okay? First of all, let's focus on this test case only. Let's print the supposedly instant sum. It is 53, yeah. It's 13 twice. Why is it so? Okay, my bad. First of all, I would like to say while ARR of IND is greater than value IND minus minus. Yeah, my bad, guys, my bad. Now, what is this? Uh, chapter 2. Yeah, we were in chapter 2. Let's hope. I'm just hoping. I have no proof of the solution, but let's give it a try if this is indeed a correct solution, and then try to justify it. And yeah, fantastic. It's wrong. You know, guys, I guess we should solve uh, this question in the next stream. Yeah, bye bye.